Hi, welcome to this video where we continue taking a look at Richard Dedekind's essay, The Nature and Meaning of Numbers, and in this video we're going to start to take a look at chapter 7, which is titled Greater and Less Numbers. So this is one of the longer chapters. It's not a very long chapter in itself, but it's relatively speaking one of the longer chapters of this particular essay, and for that reason I'm probably going to break this down into ideally 2 videos, possibly 3, but I'm going to try to fit everything into 2 videos. So as usual, I'm going to read through the contents of the chapter and I'm going to give my interpretations and explanations about what I think is going on. So let's get started with Theorem 81. So this theorem states every number n is different from the following number n primed. So remember what the notation is here. N primed is the transform of n. So n is a number, so it's a part of this simply infinite system, uppercase n, and n primed is the transform of n. So the transformation, it would typically be denoted using phi, for example, and phi would be a similar transformation. So this is in line with definition 71. Okay, so n primed is I can't remember where it's defined now. Right, okay, so definition 73, we get that the transform n primed of a number n is also called the number following n, and what we'll find further down the line, when we come to addition, for example, n primed will quite naturally coincide with what we think of as n plus 1. So the next number in the number series, in the series of natural numbers. Okay, so the proof of theorem 81 is by induction. So we've got 2 conditions that we need to satisfy. So thinking about theorem 80, which I looked at briefly in the previous video, actually there wasn't really anything to look at. It was really just, theorem 80 is really just a restatement of theorem 59. We've got 2 conditions that need to hold, rho and sigma. So in this case, we're taking n equals 1 for the case for rho, the first of the 2 conditions. So in theorem 80, we've got n equals m. It's a bit more general, but typically we take n equals 1 as our kind of start point for the induction. So if you're familiar with mathematical induction, then you'll kind of recognize what's going on here. So in the case when n equals 1, we need to show that n is different from n primed. And this is easy to show because we know that 1 is a part of n. Remember that n is equal to the chain of 1. And by theorem 40 something or other, I can't remember, let me just have a quick look. Theorem 45, a system A is always part of its own chain. So if we take our system to be equal to 1, then we know that 1 is a part of its chain, 1 naught. So therefore 1 is a part of n, but that's kind of by definition anyway. But we also know that 1 is not a part of, or 1 is not an element of n primed. Okay. Whereas 1 primed is an element of n primed. So therefore, because an element is either in a system or it is not in a system. Since 1 is not in n primed, but 1 primed is in n primed, that means that 1 and 1 primed cannot be equal. Okay, so 1 is not equal, or is different from, should I say, 1 is different from 1 primed, which is the number following 1. So I'll try to stick with Dedekind's terminology as much as possible. Sometimes I might slip up from time to time, but Dedekind specifically says n is different from the following number n primed, as opposed to n is not equal to. I suppose the two could be used interchangeably, but I'll try to stick with Dedekind's terminology. Okay, so we've got n equals 1 accounted for. So now we assume that the theorem is true for a particular number n. So assume true for number n, i.e. that n is different from n primed. Okay, so that is the effectively the inductive hypothesis. Okay, that's the inductive assumption that we're going to be making. So if the theorem is true for a number n, and we put the following number, n primed, so I'm reading straight off from Dedekind's work here, n primed is equal to p, then is n different from p. Okay, that's the inductive hypothesis coming into play. Whence by 26, on account of the similarity 71, so that's the similarity of the transformation phi, or that we're using to pass from n to n primed in each particular case. On account of the similarity 71 of the order setting transformation phi, it follows that n primed and therefore p is different from p primed. So n is different from p. So we apply our transformation to both n and p. And then if we think back to 26, definition 26, that means that because the transformation phi is similar, then we've got that n primed is different from p primed. Okay, so Dedekind doesn't really use the notation n primed primed, but that's effectively what p primed is. It's n primed primed. It's the number after the number after n, if you understand what I mean. So hence the theorem holds also for the number p following n, which was to be proved. Okay, so that's we're done with theorem 81. Okay, so let me maybe I don't need to clear any space actually. So let's just move on to theorem 82. In the transform chain n naught primed, and it's not printed very clearly, but that is n naught primed in there, of a number n, by 74 and 75 is contained its transform n primed, but not the number n itself. So again, this is another induction proof. So the theorem is true for n equals 1 because the transform chain of 1 is equal to n primed. And so where do we get that from? Transform chain of n. So yeah, I mean that's obvious, right? Okay, so I'll just go on to the next page. So since 1 is equal to n, then the transform chain of 1, which we can write by theorem 75, we can write without the brackets, is just equal to n prime. So this follows from, I guess, 22, is it? Or something like that, maybe. I can't remember it exactly. But anyway, that's what we have. And because by 71, the base number 1, so that's definition 71, condition gamma, because we know that n is by definition a simply infinite system, and therefore the element 1 is not contained in n primed, then we have that in the transform chain for 1 not primed of a number n, is contained its transform. So we've got the number 1 primed contains as an element, but the number 1 is not. Okay, so in the case when n equals 1, the theorem holds. Okay, so let's have a look now at the next condition. So if the theorem is true for the number n, so just to make that clear what that means, it's true for the number n. That means that n is not an element of n naught primed, but n primed is an element of n naught primed. So this is the effectively our inductive hypothesis. And we again put n primed equal to p. So when we see Dedekind doing this, it's again typically because he seems to want to avoid using the notation n primed primed for whatever reason. Okay, so we again put n primed is equal to p. Then n is not contained in p naught. So n is not contained in p naught because p naught, because p is equal to n primed, p naught is equal to n naught primed, and we by inductive hypothesis, therefore n is not in n naught primed, so therefore n is not in the chain of p. Therefore, is it different from every number q contained in p naught? Okay, again we've got this very clear distinction. If an object, either an object is in a system or it is not in a system, and if an object is not in a system, then it cannot be equal to any of the objects in the system. So n is different from this system. P naught consists of certain elements q, so therefore n cannot be equal to any of the q. Whence by reason of the similarity of phi, it follows that n primed and therefore p is different from every number q primed. Okay, so if we've got n is different from q, q being in the chain of p naught, and it may be the case, by the way, that q is equal to p. Okay, so I'll just put p as a little aside because this is one of the possible possibilities for q. So we apply the transformation phi to all of these, n primed, q primed, and in particular p primed. Well, n primed must be different from q primed, all of the q primed, and in particular different from p primed. But remember that n primed was set equal to p. And all of the q primes are contained in the transform chain of p naught. In other words, these are all elements in p naught primed. So because n primed is different from all of the q primes, then n primed cannot be an element in p naught primed. But remember that p naught primed is effectively, again using this notation that Dedekind doesn't really use, it's how am I going to write this? It's kind of like n naught primed. I don't really know how to write it. Maybe this is the reason why he avoids using it, because it does get kind of clumsy after a while. So therefore the theorem holds also for the number p following n, which was to be proved. Okay, so that's theorem 82 done. Okay, so just while I clear a little bit of space here, I'd be really grateful if you would consider subscribing to the channel if you haven't done so already, and if you wouldn't mind hitting the like button for this video. It really helps my videos show up in more YouTube searches, although I'm not sure how many people actually search for videos on this particular work, but if they do, then it'd be really useful, I guess. So I'd be very grateful if you would hit the like button for this video. Okay, so Theorem 83. The transform chain N0 primed is a proper part of the chain N0. So this the proof follows from 76, 74, and 82. So 76, what does that say? Right, so 76 says that N0 primed is a part of N0. This is going to be a really useful property, actually, by the way. Something to bear in mind constantly as we go through this chapter. 74 says that every number n is contained in its chain N0, and by the condition n is right. Okay, so every element is contained in its chain. And 82, okay, so where's 82? That's what we've just proved, isn't it? So in the transform chain, N0 primed, n, okay, so n is not an element in N0 primed. So putting all of this together, what we see then is that there is an element n which is in the chain of n, but which is not in the transform chain of n. So in other words, N0 primed, it's a part of N0, but there is an element n which is not an element of N0 primed, but which is an element of N0, and therefore N0 primed is a proper part, by definition, of N0, which is what we needed to prove, right? Okay. So what's the next theorem? Theorem 84. From M0 equals N0, it follows that M is equal to N. Since by 74, so that was N is a part of its own chain. By 74, oh yeah, M is contained in M0, and therefore we've got M0 equal to N0, which is the system compounded of N and N0 primed. Since by 74. Okay, so we've got M is an element of M0. Then if the theorem were false, M is contained in M0 and... Okay, so, if the theorem were false and hence M different from N... Aha, okay, right, yeah, I see. So, M0 equal to N0 equal to the system compounded of N and N0 primes. That means that any element of M0 must be either equal to N, so either M is equal to N, or M is an element of N0 prime. So remember the definition of a system compounded of a series of other systems. In this particular case, we've got two systems, one system of which is composed of a single element, and that's the system N. So if we're denying that M is equal to N, in other words, we're saying M is different from N, then we don't have this case, right? So therefore, M must be an element of the transform chain of N. Hence, by 74 also, M naught. So what's the condition? M is a part of n naught primed. The condition, right? Okay, so M is a part of n naught primed by 74 is equivalent to the the chain of M is a part of the transform chain of n primed, i.e. n naught is a part. Right. Okay. So because we're assuming that m naught is equal to n naught, then it follows that if m naught is a part of n naught primed, then n naught is also part of n naught primed. And that's a contradiction to 83, which says that the transform chain n naught primed is a proper part of the chain, is a proper part of the chain n naught. So if it was just that the transform chain, going back to theorem 83, if it was just that the transform chain n naught primed was a part of the chain n naught, that could open up the possibility that they're equal. But because n naught primed is a proper part of n naught, then we've got that n naught primed is a part of n naught, but not n naught is a part of n naught primed. We don't have this second case. So we've got a contradiction there. This is our contradiction. Hence, our theorem is established. In other words, m naught, the chain of m equal to the chain of n implies that m is equal to n. Okay, so theorem 85. Let's have a look. If the number n is not contained in the number chain k, then is k a part of the transform chain of n. So let's have a look. Let me clear a little bit of space for this one. Okay, so by 78, the theorem is true for n equals 1. So let's have a look at the case n equals 1. Remember, if it's by induction, we've got these two conditions, rho and sigma, that we need to satisfy. So if the number n is, so if 1 is not contained in the number chain k, so remember, if k is a number chain, then it's effectively a chain of the form m naught, where m is a number. Okay, so we think about k as something of this form, where k is some particular number. Is not contained in the number chain k, then by 78, so let's have a look what 78 says. So 78 says that, that n is equal to 1 n primed. So that's 78. Hence every number different from the base number 1 is element of n primed, i.e. transform of a number. So in this case, we've got 1 is not contained in k. Sorry, I'm just putting it together here. So n equals the system compounded of 1 and n primed, hence every number different from the base number 1. So k is a number chain, then every element of k. Sorry, I'm just trying to think this through. I'm sure it's really obvious. I'm probably overcomplicating things, but so k is a number chain. Let me get this straight. So k is a number chain. So every element of K is an element of N. So if M is an element of K, then either M equals 1. Right, okay. Of course, yeah. Okay, so either M equals 1 or M is a part of, so every element M of K, or M is a part of N primed, which is, yeah, okay, maybe, is that what needs to be thinking? Right, okay, but M is not equal to 1, right? Because we're assuming that 1 is not contained in K, so M is not equal to 1, so therefore M, right, that's it, of course, yeah. So M must be an element in N primed. So if M is an element of N primed, and M was just an arbitrary element of K, that means that K is by definition an element of N primed, which is, of course, equal to the transform chain of 1. Okay, so remember what is meant by a part, a system being a part of another part. So what we've shown here is that every element of K must also be an element of N primed. Okay. I think I probably made that more complicated than it needed to be, but at least I've got it. I'm satisfied with that explanation, at least. Okay. Oh, I don't really need to clear this, do I? I'm going on to the next page anyway. So if the theorem is true for... I'll go on to the next page now. So if the theorem is true for a number n, then it is also true for the following number p equals n primed. For if p is not contained in the number chain, so p not contained in the number chain k, then by n, then by 40, n also cannot be contained in k. So what's 40? Theorem 40 is that if A is a part of a chain K, then is also a primed. Right, okay, so P, right, so we've set P equal to N primed. So in other words, N primed is not contained in the number chain K. So in particular, K is a chain. So N primed is the transform of N is not in the chain K. So it's kind of the contrapositive of 40, right? So 40 says that, and I'll use the notation from here. So N, part of a chain K, part of a chain K. This implies that N primed, part of K. So I've replaced the uppercase A in theorem 40 with N. So now if we use the contrapositive of this, so N primed is not a part of K, this would imply that N is also not a part of K. Okay, so it's the contrapositive argument. So if N is not a part of K, then the inductive hypothesis allows us to say that K is a part of N naught. The inductive hypothesis is that if the number N is not contained in the number chain K, which we've shown, then K is a part of the transform chain of N. Now, since by 77, what does 77 say? Is that, okay, so the number chain, so the chain of N, is it N or is it N primed? n naught primed. So it's n naught primed. The number chain, the transform chain of n naught primed is going to be equal to, which is k, is equal to the system compounded of. It's okay. So again, we've got to think we're using p as n primed, so it's p and the transform chain of p naught. So you can think about p as n primed and p naught primed as, again, it's this kind of clumsy notation, n naught primed. I think I understand now why Dedekind doesn't use why he constantly replaces n primed with p in this context. So let's stick with Dedekind's notation. It is less clumsy. P is not contained in k. So that's what we've got up here. So P is not contained in K. No, sorry, I've made a mistake. It's not K is equal to this. It's K is a part of. Equals K is a part of P naught primed. Sorry, I've made a mess here, haven't I? Right, let's try this again. So let me follow what Dedekind is writing a bit more closely. So we've got n naught primed is equal to p naught. Okay, I'm happy with that because we know that p is equal to n primed. P naught is equal to, so this is 77. It's equal to p and p naught primed. And k is a part of n naught primed. Right, okay. So in other words, k is a part of. So I was getting a bit carried away with everything. But p is not contained in the number chain k. So therefore, k must be a part of p naught primed. Okay, so kind of scratch that. Then must, so p is not contained in k, then must k be a part of p, which was to be proved. I can't remember what was to be proved, to be honest with you. If the number n is not contained in the, right, okay, yeah, so we assumed that n primed is not contained in the number chain k, and what we found is that k is a part of effectively n naught primed. And we used the inductive hypothesis. The inductive hypothesis came in here. So n primed is not a part of k, then that guarantees that n is not a part of k, and therefore k is a part of, by the inductive hypothesis, which allows us to make that, to go from n is not a part of k to k is a part of the transform chain of n. Okay, so we've got that k is therefore part of, what was it? N naught primed. Sorry, p naught primed, which is what we needed to show. Okay, so theorem 86, once I've cleared a little bit of space, that is. Okay, so once again, if you've not already subscribed to the channel, please feel free to do so. If there's anything that I'm saying that's not clear in these videos, as usual, I'm doing this video unscripted. I've got a few kind of simple notes on the page in my book, but generally speaking, I've just set up the microphone and I've got my writing pad here, and I'm just talking really. So sometimes I don't necessarily explain things very clearly. If there is anything that I don't explain very clearly, then please let me know, and I'll be more than happy to clarify any difficulties. Okay, so theorem 86. Let's have a look. If the number n is not contained in the number chain k, but its transform n primed is, then k is equal to the transform chain of n. So proof, since n is not contained in K, so n not contained in the number chain K, so that's my assumption. Then by 85, which we just proved, let me just double check, number n is not contained in the number chain K. Yep, then K is a part of the transform chain of n. And since n primed is where was I? Since n primed is a part, is an element of K, then by 47 is also the chain of n primed, a part of K, because K is a chain. So any system which is part of a chain, then the chain of that system is also part of the chain. And hence, so we've got K is a part of n naught primed, and n naught primed is a part of K. Putting these together using theorem 5, I think it's had theorem 5 and theorem. I think theorem 5, K is equal to n naught primed, which was to be proved. Theorem 87. In every number chain K, there exists one, and by 84, only one number K, whose chain K0 is equal to K. So let's have a look at this one. So if the base number 1 is contained in K, so 1 is contained in K, then by 79, which is n is the only number chain containing the base number 1, so therefore we've got that it follows that K is equal to n, which of course is equal to the number chain corresponding to 1. So in the opposite case, in other words, in the case where 1 is not in K, so 1 not in K, let Z be the system of all numbers not contained in K. Okay, so we've got this new system Z, and this is all numbers contained, not contained in K. Not contained in K. So naturally, because K is a number chain, we're thinking about K as a part of the number series n. So when we say Z is all numbers not contained in K, this makes sense. Z is also going to be a part of the number series, but as we'll see, Z is not will not be a chain. So Z is the system of all numbers not contained in K. Since the base number 1 is contained in Z, but Z is only a proper part of the number series n, then by 79, Z cannot be a chain. Okay, so if Z were a chain, then it would be, it might be a proper part of n, but it would, because Z contains 1. Okay, Z contains 1 because 1 is not in K. So therefore, if Z is a chain and it contains 1, then by 79 it must be equal to n, which is not the case. Okay, because Z, as we see, is a proper part of n, so it can't be equal to n. So Z primed cannot be part of Z, otherwise Z would be a chain. So Z primed not part of Z, because remember, a chain is such a system, it would satisfy Z primed is a part of Z, which we don't have. Okay, because Z is not a chain. Z primed cannot be part of Z, hence there exists in Z a number n whose transform n primed is not contained in Z, and is therefore certainly contained in K. Remember that Z is the system of all numbers not contained in K. So if we find a number n, which is part of Z, but when we apply the transform to n, we get n primed, which is not a part of Z, then because Z is all numbers not contained in K, then n primed not being in Z means that n primed must be in K, and hence not in Z. So n primed is certainly contained in K, and since further n is contained in Z and therefore not in K, then by 86, what was 86? If the number n is not contained in the number chain K, but its transform is, then K is equal to the transform chain of n, and hence K is equal to n primed, which was to be proved. Okay, so yeah. Right, okay, so that means therefore that K naught, the number chain corresponding to the number K, is equal to uppercase K. Okay, so theorem 88, if m and n are different numbers, then by 83 and 84, one and only one of the chains, m0, n0, is proper part of the other, and either n0 is a part of m0 primed or m0 is a part of n0 primed. Okay, so clear some space again. I'm sure there's a quicker way for me to do this. In fact, let me try something. There we go. How's that? Okay, so if n is contained in m0, so n is so we're on to theorem 88 here. N is a part of m0, and hence by 74, because m0 is by definition a chain, it's the number chain corresponding to m, then n0 is a part of m0. Then m cannot be contained in the chain n0. Okay, so if m, so let's have a look what happens. If m is a part of n0, then in that case, because n0 is also a chain, we'd have m0 as a part of n0. Putting these two together would give that m0 is equal to n0, and then 74, sorry, not 74, 84 would say that m is equal to n. But we have, by assumption, that m is different from n. M and n are different numbers. Okay, so if we start with n is a part of m0, then we have n0 as part of m0, but we see that m, the element m, which is a part of m0, cannot be a part of n0, and therefore n0 must be a proper part of m0. If that makes sense. And then it follows by 85. What was 85? The number n is not contained in the number chain K. Then K is right. So n is not. So m is not contained in the number chain n0. So using the notation from 85, n0 is, I've replaced K with n0, and I've replaced the n of theorem 85 with m. Then we get that n0 is a part of m0 primed. Okay, so that's from 85, yeah. In the contrary case, when n is not contained in the chain m0, we must have by 85 that m0 is a part of n0, which was to be proved. Okay, so nice and easy. Aha, definition 89. The number m is said to be less than the number n, and at the same time n is greater than m. So if we've got the symbols, m is less than n, or alternatively n is greater than m. When the condition n0, the number chain of n, is a part of the number chain, the transform chain of m. So this is really important, okay? You got to look at this very closely. This is making a comparison between the number chain of n and the number chain of the transform chain of m. So this is not making a comparison between n0 and m0. It's making a comparison between n0 and m primed naught. So the significance of this is that if n0 is a part of m0 primed, it may be the case that n0 is equal to m0 primed. Okay, so this does not in and of itself mean proper parts, that n0 is a proper part of m0 primed. In fact, we don't require n0 to be a proper part of m0 primed. But we do need to ensure that n0 is a proper part of m0. Okay, now bearing in mind that m0 primed is a proper part of m0. Okay, so this was, I said this was going to be useful earlier, didn't I think? I can't remember where. But, yeah. Well, I mean, it's Theorem 76, from Theorem 76. Because m0 primed is a proper part of m0, therefore, if we've got that n0 is a proper part of m0 primed, that will guarantee that n0 is a proper part of m0. Okay. So this definition is quite significant in that respect. It's fulfilled, which by 74 may also be expressed that n, so this is equivalent to n is an element of the transform chain of m. Okay, so that's the obviously quite an important definition. And then we've got Theorem 90, which gives three possible cases. If m and n are any numbers, then always one and only one of the following cases, lambda, mu, and nu, occurs. So lambda is that m equals n equals m. In other words, the chains, their respective chains, are also equal. Mu, which is that if m is less than n or n is greater than m, then the chain of n is a part of m0 primed. So that's mu. And then we've got nu, which is m is greater than n or n less than m. Then we've got that m0 is a part of n0 primed. Okay. So if lambda occurs by 84, then can neither mu nor nu occur, because by 83 we never have. Okay, so if lambda occurs, so in other words, m0 is equal to n0, right, okay, so n0, so this is lambda. So if we start with lambda, for mu to occur, so big exclamation marks here next to this, I guess, because we're just trying something out here. So if mu also holds, then we've got n0 is a part of effectively n0 primed. Because remember, n naught and m naught are equal. So if we've got n naught is a part of m naught primed, well, this would be n naught primed. That follows from, I guess, back at 22 or 23, maybe. Something like that. So that would suggest, therefore, that n naught is a part of n naught primed, which doesn't occur. Okay, so what's that by 83? What does 83 say? The transform chain n naught primed is a proper part of the chain n naught. Okay, so we can't have that. On the other hand, if we have that m naught is a part of n naught primed, again, m naught is equal to n naught, we get the same thing coming up. N naught is a part of n naught primed, which can't happen. Okay, so if lambda occurs, mu and nu are excluded. If lambda does not occur, then by 88, so in other words, m and n are different numbers, then 88 says one of those cases, either, so if m and n are different, then we've either got n naught is a part of n naught primed, or m naught is a part of n naught primed, but we can only have one or the other. We can't have both simultaneously. So that proves theorem 90. Okay, so let me try my little trick again. Ah, that's much faster. Okay, so theorem 91. N is less than n primed. That's what we need to prove. For the condition, for the case nu in 90 is fulfilled by m is equal to n prime. So if we set m equal to n prime, then remember, of these conditions in theorem 90, only one can hold, and it doesn't matter if we okay, let's try out nu, condition nu, because that's the one evidently that's fulfilled, and let's see how it's fulfilled, and then I'll explain why we don't even need to bother checking the other ones, right? So if m is equal to n primed, then we have that m naught is equal to n naught primed, because that's from lambda, by the way. So that's not nu that I've used there, that's lambda that I've used there to arrive at this conclusion, that the chain of m is equal to the chain of n primed. Okay, but remember, m is equal to n primed. So in particular, by the way, we've got that m naught is a part of n naught primed. And because m is equal to n primed, then we get that n naught primed is a part of n naught primed. Oh, that didn't go very well. Which is true. Okay, so the condition for nu is satisfied. Okay, so now if we think n naught primed is a part of n naught primed, then m naught is a part of n naught primed, so that matches up by nu to the case where we've got m is greater than n. But remember that m was equal to n prime, so therefore n primed is greater than n, or alternatively n is less than n primed. Okay, so now I don't even need to bother checking whether either of the other cases, mu or lambda, hold. I've seen that in the case when m is equal to n primed, nu holds. So the other two cases are automatically excluded by theorem 90. Okay. So that's the proof of theorem 91. So let's have a look at definition 92. So to express that m is either equal to n or less than n, hence not greater than n, we use the symbols m is less than or equal to n, or n is greater than or equal to n. And we say that m is at most equal to n, and n is at least equal to m. Okay, so fairly typical notation. Right, so theorem 93. Each of the conditions, m is less than or equal to n, m is less than n primed. Okay, so maybe I should use Dedekind's terminology. I'll probably forget to do this, but m is at most equal to n, m is less than n primed, or the chain of n is part of the chain of m. So each of these conditions is equivalent to each of the others. For if m is at most equal to n, then from lambda and mu in 90, we always have right. Okay, so if we check lambda, if m is this is the case when m is equal to n, then we've got m naught equals n naught, and what was the other one? Mu. That's when m is less than n. In that case, we've got, let me get it right, n naught is a part of m naught primed. We always have that n naught is a part of m naught. Right, okay, so because if we turn our attention to the first one, m naught equals n naught, then we clearly have that n naught is a part of m naught. And if we turn our attention to the second one, where we've got n naught is a part of m naught primed, we also have that m naught primed is a part of m naught. So putting these two together, using theorem 7, we get that n naught is a part of m naught. Conversely, sorry, because by 76, m naught primed is part of m naught. Conversely, if n naught is a part of m naught, and therefore by 74 n is a part of m naught, it follows from m naught equal to the system compounded of m and m naught primed, that either n is equal to m, or n is a part of the transform chain of m. If n is a part of the transform chain of m, then n naught is a part of m naught primed. Okay, because m naught primed is a chain. So in this case, we've got n is greater than m. So if we've got that n naught is a part of m naught, then either n is equal to m, or n is at least equal to m. No, sorry, no. N is greater than m, and therefore n is at least equal to m, or m is at most equal to n, whichever you prefer. So we've shown that the two conditions, m is at least equal to n, and n naught part of m naught are equivalent. What about the last one? Let me just clear a little bit of space. Oh. Okay, so hence the condition, right, yep. So besides, it follows from 22, 27, and 75 that this condition, n naught part of m naught, is again equivalent to n naught primed is a part of m naught primed. So that's 22, I think. Let me just check. Yeah, that's 22. What's 27 say? I've forgotten what 27 says. Oh, right. 2775 I by mu. In 90. M is, let me have a look at mu is. M is less than n primed, which was to be proved. So as it follows that this condition is again equivalent to, right? So these are equivalent to each other. So therefore, yeah, okay. So we've got the equivalence between these conditions here. Okay, right. Yeah, I'm happy with that. So finally, not finished yet. So I'm probably going to go up to, try to get up to theorem 97, I think. Because then 98 is a definition, and I think I will take it from there in the next video. So 94. Each of the conditions n primed is at most equal to n, n primed is less than n primed, and m is less than n is equivalent to the others. This proof follows immediately from 93 if we replace in it m by n primed. Okay, so in 93 we've got m is less than n prime, so we replace what we're doing, replace m with n primed. So we know that these two are equivalent, and from it mu in 90. This proof follows from 93 if we replace it by m by n primed, and from mu in 90 was mu. I don't know actually. How does that follow? N primed is less than n primed is less than n primed. I'm not sure. I'm gonna have to come back to that one. I can't think right now for that one. I'll have to come back to that one. Okay, so let's move on to 95. Let's forget about that one for now. I just can't think off the top of my head. Again, it's probably really straightforward. It's just because I'm doing this kind of off the cuff. Sometimes I don't see exactly what I need to see, even though sometimes it's really obvious. So L is less than M. M is less than or equal to N. Or if L is most equal to M and M is less than N, then is L less than N. And if L is at most equal to M and M is at most equal to N, then L is at most equal to N. From the corresponding conditions 89 and 93, so let me check those. 89, the number M is said to be less than. Okay, so in the case where L is less than M, then 89 says that L is less than M. L less than M, then M is part of L naught primed, and M less than is at most equal to N. This is by 93. Yep. Okay. So N naught is a part of M naught. Putting these two together using transitivity theorem 7, we get that N naught is a part of L naught primed. And okay, similarly, the same thing comes also from the other conditions. So if we go for these now instead, we'll get a very similar situation arising. The same thing comes also from M naught is a part of L naught, and N naught is a part of M naught primed. because okay, so let me go through these a bit more carefully then. So L is at most equal to M. So in that case, by 93, we've got that M naught. Am I getting this the right way round? Yeah, is a part of L naught. We've also got that M is less than N. So M is less than N. That means that N naught is a part of M naught primed. But we know that M naught primed is a part of M naught. So therefore, again, using kind of transitivity, this would tell us that N naught is a part of M naught. And then using transitivity with this and this, we'd get that N naught. Is that right? Finally, M naught is a part of. But we also have that M naught. Did I miss something off somewhere? We have also. Oh, sorry, I've made a mistake, haven't I? M naught is a part of L naught. Right. No, sorry, I've made a mistake there. So actually, it should have been. It should be. I should be looking at this a bit more closely. M naught is a part of L naught. That means that M naught primed is a part of L naught primed. And now use transitivity on these two to get that N naught is a part of L naught primed. So both of these, which arise from the two different cases that we've just looked at, corresponds to L is less than N by mu of theorem 90. Whoa. And then finally, from M naught is a part of L naught and N naught is a part of. Right, okay, so that's straight from theorem 7. So using theorem 93 for each of these, and then theorem 7, we get the result. Okay, so theorem 96, and I'll go on to the next page now. In every part T of N, there exists one and only one. So every part T of N, so T doesn't have to be a chain. Okay, so T is a part of N. T not necessarily a chain. Oh. Not necessarily a chain. There exists one and only one least number k, i.e. a number k which is less than, according to definition 89, every other number contained in T. If T consists of a single number, then is it also the least number in T. Okay, so since T naught, so T is not necessarily a chain, but T naught is a chain. Then by 87, where's 87? In every number chain K, there exists one, and by 84, only one number K whose chain. Okay, so there exists one. So T is because T is a part of N. The chain of T is also a part of N. So this is, I can't remember which theorem this is, but because N is a chain, T is a part of a chain n, therefore the chain of T is going to be a part of the chain n. So therefore by 87 there is a number k such that the number chain of k is equal to T0. Since from this it follows by 45 and 77 that T is a part of, so what's 45? I think that says that T is a part of T0, A is a part of A0. So T is a part of T0, but T0 is equal to the system compounded of K and the transform chain of K, so that's 77. Then first must K itself be contained in T. Okay, so that's, why is that? Follows that T is then must, because otherwise T would be contained in the transform chain of K, and hence by 47 also the transform chain. Aha, right, okay, so if K not in T, then T naught is sorry, T or T naught, T is a part of the transform chain of K. Because K naught primed is a chain, then T naught is a part of K naught primed, and therefore because we know that T naught is the system compounded of K and K naught primed, and therefore K is an element of T naught, but now we're showing that T naught is also part of K naught primed, then that means that K, which is an element of T naught, must actually be an element of K naught primed. But that's a contradiction by 83. So K is a part of T. So we don't have this happening. So K is a part of T. Besides, every number of the system T different from K must be contained in K naught primed. Yeah, so, okay, right, fine. Yeah, so T is part of T naught, which is the system compounded of K and K naught prime. So any element of T must be an element of T naught, and hence must be an element, it must be either equal to K or an element of K naught primed. But any element of K naught primed is going to be greater than K. Once from 90, it follows that there exists in T one and only one least number, which was to be proved, and that's K. Theorem 97, the least number of the chain N0 is N, and the base number 1 is the least of all numbers. For by 74, what's 74? Is that every number N is contained in its chain. 74 and 93, the condition M is a part of N0. So M is a part of N0 is equivalent to M is greater than or equal to N. Okay, so 93, M is greater than or equal to so N by 74, N is a part of N0, and by 93, M is a part of N0. Okay, so if M is a part of N0, then M0. Okay, so yeah, sorry. Theorem 74 also follows that M0 is a part of N0, and therefore by 93, this is equivalent to. I've got to get this the right way round. N is at most equal to M, or alternatively, because it's the other way around here, M is at least equal to N. so we didn't really need that actually. Or our theorem also follows immediately from the proof of the preceding theorem, because if in that we assume t equals n naught, then evidently k is equal to n. By 51, what does 51 say? 51. If a is a chain, then a naught is equal to a. Okay. I've actually not thought much about that last bit. Our theorem follows. I need to have another look at that. I can't remember off the top of my head what I've. Maybe I'll look at that again in the next video. So I can't think off the top of my head right now. Okay, so that brings us to the end of this video. A couple of little blips in this video, but I don't think I've done too badly, I hope. So thank you for watching. If you've managed to make it to the end of the video, if there are any points that you'd like me to clarify, please let me know in the comments section, or if you prefer, get in touch with me directly. The next video, I'll continue from definition 98, and I'll maybe explain the end of this theorem 97, and I can't remember what was the other one that I had a little bit of difficulty with. I can't remember, but I'll clarify those points hopefully in the next video, provided that I remember. So thank you for watching, and I will look forward to seeing you in the next video.